Hello and welcome back to the next video in the series on nodal analysis. So in the past video, we started doing nodal analysis on this circuit and we assumed our different current directions. We also named those different current directions. We also colored in our different nodes and we named those. And we also got to write our current in equals the current out equation for our first node, which we called V1. So this was the equation we got. So now what we're going to do, we're actually going to do the same exact thing that we did back when we did the less complicated circuit. And essentially what we're going to do is this. We're going to think about just an arbitrary resistor. If I have a resistor that has a resistance R, and I apply a voltage at this end that I call VA, and a voltage at this end that I call VB, and I want to know, and I define a current I that flows across it. If I rewrite Ohm's law, so the voltage across a resistive element is going to be equal to the current through that element times the resistance of that element. What I really care about this is the voltage difference across that element. And as you can see in this equation I've got current on both sides of this equation, right? This is all in terms of current, all in terms of amps, right? So I'm going to just rearrange Ohm's law, just like I did in the last circuit, to solve for the current. So voltage difference divided by resistance is going to be equal to our current. So now if I take this situation where I apply a voltage VA to one side and a voltage VB to the other, that voltage difference for a current to be created, the current, we always define the current to flow from the higher side of the voltage to the lower side of the voltage. The current flows from a positive voltage to or I shouldn't say a positive voltage to a negative voltage, it flows from a higher voltage to a lower voltage. So if I want to rewrite that voltage difference across my resistor here, that is going to be equal to VA minus VB. That's going to be the voltage across my resistor. So now if I divide by the resistance, my resistance R, that will give me the current through that resistor. So that's going to give me the current through that resistor. So now let me start with I1. Well, I1 is going through, it's not going through a resistor, right? It's going through a voltage source. So I can't really do that with I1 right now. I'm going to have to relate I1 to this circuit a little bit differently. I'm going to leave I1 alone for right now. I'm just going to leave it as I1. And I'm going to say, let me just reverse this so I've got I2 plus I3. I'm just reversing the order. Or else actually no, I'm going to leave this as I3 and I2. So let me go ahead and I'm going to rewrite this current I3. So I3 is going to be equal to the voltage difference across this 6 ohm resistor, and this current I3 is going to flow from V1, so that is the higher voltage for our current I3, to the lower voltage, or the lower assumed voltage, V0. So it's going to flow from plus to minus across this resistor. So the plus side of the voltage, just like we assumed that VA was the plus side of the voltage here and VB was the minus side of the voltage here, the plus side of the voltage on this 6 ohm resistor is going to be V1. So we're going to have V1 minus V0, and we are going to divide that by our resistance. Divide that by 6 ohms. So now we've rewritten we've rewritten that current I3 in terms of V1 and V0. We've rewritten it in terms of voltages. So now I'm going to go ahead and do the same thing for my current I2. So I2, if it's flowing from left to right, I'm going to assume that this is going to be the plus side of the voltage because the current is going to flow from the plus side to the minus side. And notice, like, I2 was the current that I just kind of reversed on a whim. If I flip this current around, then this would be the positive side, this would be the minus side. It would be like multiplying what I would get by -1. So hopefully you can see that, it doesn't matter which direction I assume these currents to be in. It's, I just still write my equations the exact same way. But now for this current I2, it's flowing from V1 to V3, the V3 node. So my positive side, my plus voltage, is V1. So this is going to be plus V1 minus, the minus side of the voltage is V3. So V1 minus V3. That's my voltage difference across this 4 ohm resistor. And now I'm going to divide by the resistance of that resistor. So divided by 4. And there we go. I've rewritten my currents I3 and I2 in terms of a voltage difference divided by a resistance. And I've just kind of left I1 alone for right now. I1 I can't really do that with. I'm going to have to figure out what I1 is in a bit of a different way. So now I've got, that's my first equation that's kind of that's been written. Let's actually go. Let's actually really quick. We are going to rearrange this equation, and I'm going to rearrange this equation. Actually, you know what? No, we're going to leave this equation just the exact same way it is, the exact way it is right now, and we are going to rearrange it a bit later on in the video. So now let's go ahead and write our second equation. So this first equation described our node V1. So how about for the second equation, let's describe our node V0. Let's write our current in equals current out equations for the node V0. So now V0, what goes into my V0 node? And notice I want to know what goes directly into V0. I want to know what starts in a different node and ends up in V0. So I could kind of say like I2 goes into V0, right? Like all the current that flows into this node V3 from across that 4 ohm resistor, eventually it's going to make it into my V0 node. But it doesn't flow directly into V0, right? I only want to worry about currents that are flowing from another node into V0. That's what I mean when I say current that goes into my node V0. So I3 is going to flow in, right? It starts in V1, flows from left to right across the 6 ohm resistor, and it ends up in V0. So I3 flows in. So I3 flows in. And I0 flows in, right? It starts in the node V3 and it ends up in the node V0. So it flows from V3 into V0. So it flows into V0. So plus I0. And then that's going to be equal to all of the current, the sum of all of the currents that flow out of my node V0. And it looks like I only have one of those, right? I4 flows from V0 out into my ground node. So that is equal to I4. Notice, 1 amp and kind of I1 are also, you could think about it, sort of flowing out of V0, but they don't flow directly out. When I say the current out of my node V0, it has to start in the node V0 and flow into a different node. That's what I mean when I say the current out of that node. So hopefully that's clear. The people I've tutored this week, that's been a little bit unclear. Some people have had a little bit of trouble with that, but hopefully that's clear. I'm talking about currents that start in V0 and flow to a different node, that flow out to a different node. So now I've got all of these different currents, and let's just do the same thing. Let's rewrite these three currents in terms of a voltage difference divided by a resistance. So I3 is pretty easy. In fact, we already did it, right? I3 is going to be V1 minus V0 divided by 6. So I3, V1 minus V0 divided by 6. That's what I3 is. Plus I0. I0 is going to, if our current is flowing from left to right, that's our positive side of the voltage, that's our negative side of the voltage. So the plus side is V3, so we're going to have V3. Let me actually change colors so I can keep this kind of color coding going. So I'm talking about I0 here. So the plus side is going to be V3, so that's V3. The minus side is going to be V0, minus V0. And we're going to be dividing by our resistance, which is 12 ohms. So divide by 12. And all of that is going to be equal to the current that flows through this 15 ohm resistor, I4, that flows from top to bottom. So the positive side of this voltage is going to be V0, our V0 node, and the minus side is going to be our ground node, right? It's just going to be 0 volts. So this current I4 is going to be equal to V0, the plus side, V0 minus 0 volts, minus 0, divided by our resistance, divided by 15 ohms. And that's our second equation. So now we've got two equations that we've got written. And remember, we've got 1, 2, 3 nodes that are not the ground node, right? We've got 1, 2, 3 nodes. So we're going to need one more equation if we want to completely describe this circuit. So let's go ahead and we're going to rewrite, we're going to write an equation for this node, our V3 node. So now our V3 node is going to be, let's do this, 3. Our third equation is going to be the current into our node V3. So it looks like I2 flows into V3. I2 flows from V1 into V3. And the positive side of that voltage is V1. We've even done this before, right? We did it up here. So the positive side of that voltage for, before we do that, we should actually just go ahead and write this down for each of the currents. So I2 flows into V3. And also 1 amp flows into V3 too, right? Because we have this ideal independent current source here. So 1 amp flows in, so I2 plus 1. And that's going to be equal to our current I0, because I0 is the only thing that flows out. So that is going to be equal to our current I0. So now let's just go ahead and rewrite these currents, kind of just like we've done. We actually have done this already for both of these currents. Let's go ahead and rewrite each of these currents in terms of a voltage difference divided by a resistance. So I2 is going to be V1, that's the positive side of the voltage, minus V3 divided by 4 ohms. It's going to be V1 minus V3 divide by 4 ohms, plus 1, the 1 doesn't change, equals I0. I0, the positive side of the voltage, is V3. V3 minus the negative side of the voltage, which is V0, minus V0. And then we're going to divide that by the resistance. We're going to divide that by 12. And that's pretty much it. We've got all of our different equations here. There's only one more thing that we kind of want to mention. We have got how many equations? Just go ahead and look at what we've got. So we've got one equation right here. Let me actually here. I don't want that to be a minus sign. Let me draw that as an arrow. That kind of looks too much like a 7. So I'm going to say that's our first equation. We've got one equation right here. We've got our second equation right here. And we've got our third equation right here. I want you to pause the video really quickly. I want you to look at these 3 equations that we've got. And I want you to count how many unknowns do we have in these 3 equations. Just count them up. How many unknowns do we have? Hopefully you can see we have got 3 different equations, but we have actually got 4 unknowns in these 3 equations. So if you remember from algebra or perhaps linear algebra, if we have 3 equations, we can solve 3 equations for 3 unknowns, right? We can't solve 3 equations for 4 unknowns and get like definite answers, right? We can't get exact answers if we have 3 equations and 4 unknowns. I'm out of time in this video, but I claim right now that we actually know one of these unknowns. So we've got our unknowns V1, V0, V3, and I1, right? Or V1, V0, V3, and I1. So we've got 4 different unknowns here. But I claim that we actually already know what one of these unknowns is. So it's not like we're going to have to write another equation. We already know what one of these unknowns is. I'm going to stop this video here. Before you start watching the next video, try to figure out what the one unknown is that we know already. What is the one unknown that we have out of I1, V0, V1, and V3 that is actually already known, that we can already say exactly what it is? So anyway, thanks for watching, and I will see you in the next video. See you soon. Bye.